Hey, good morning, everybody, or good afternoon. Today's YouTube video is going to support our Friday, April 10th lecture that's posted as a PowerPoint on Canvas. Got a few announcements on there. You have a sapling assignment due Friday, April 10th. You have another one on April 16th that deals with electrochemistry. And I will prepare one more that'll be due on April 20th, the last day of the lecture, of the course, the semester. And that'll deal with redox titrations and chromatography, what we've been going over in our past lecture or two. The topics that we're discussing today are in chapter 7 and 12 in your text from Harvey. And I'm also using chapter 22 from Harris to help supplement our discussion. There are two categories that we're going to be discussing in some detail today about column chromatography. And these two broad categories of how we classify chromatography depends upon the mobile phase. One type of chromatography that we'll spend some time on a little bit later is gas chromatography. This is the situation in which we have a gas mobile phase that carries our solute over a column. And in that column, we have a stationary phase that's composed of either a solid support or a solid support with a liquid coating on it. The type of chromatography that we're going to spend a lot of time on in the first part of our chromatography section is liquid chromatography. This is called LC. In this case, liquid is the mobile phase. We're going to carry our solute or components through a column. And once again, our column has a solid or a liquid stationary phase associated with it. So when we think about chromatography, there are a variety of mechanisms that can encourage the separation process. And as I said, we're going to look a little bit at liquid chromatography as our first stage of understanding about chromatography, the separation process. And so one mechanism that we've already discussed in our extraction section is partitioning. And let's understand that the partitioning mechanism is similar to what we discussed for an extraction. And let's think about what happens maybe on a microscopic level in an LC experiment. LC, liquid chromatography. Let's draw the solid support just to help us understand. So let's just imagine that this is our column. And there's a surface within the column itself. And the column has solid particles on it. And we'll just make a column where it has two sides to it. So there's an idea of what our column looks like. This is the internal portion of our column. And along these solid support particles, there's a liquid coating. So there's a liquid coating. So essentially what we have is we do have liquid-liquid interaction. And so what happens during the course of introducing a liquid mobile phase, which is carrying our analyte, which might be interacting with other species that we want to separate it from, we introduce our liquid down the column. And our liquid is carrying our analyte in it. So just like we discussed in partitioning that we did for an extraction, let's blow up this view a little bit. Let's look right here at that guy. And let's expand the view so we see what happens. So here's our liquid that's on the surface of a solid support. And here's our liquid that's our mobile phase carrying our analyte. Well, what happens is our analyte will partition into and back out of the liquid phase that's on the solid support and back into the mobile liquid phase that's moving through the column. And it's this partitioning, this equilibrium, such as we discussed last time, which encourages separation. If we have two species that are traveling through our column, one species will most likely, or if our separation strategy is set up correctly, will have a different equilibrium than another species that's traveling through the column along with it. As the two species equilibrate differently between the mobile liquid phase and the stationary coated phase that's liquid, well, then we can encourage separation of these two species. Now, that's sort of a dynamic, bigger picture of what's happening. Let's move to understanding it using some columns and what we might see in an experimental condition. Because once again, there's some terminology that we need to understand. And we're going to think about now an experiment where we're going to use that setup. So this is a liquid chromatography and LC experiment. And what we're going to do is we're going to have a column. And our column has a solid support. So we'll just draw these little dots that represent solid particles that are coated with a liquid, such as we showed in our last blown up image. And now what we're going to do is we're going to allow a sample, a liquid sample, to sit on top of the column. And this liquid sample has two components in it. We'll call one A. I'm giving it green because I don't have any other kind of marker other than green. Oh, I think I do have a red one. A and B. Yes, I do. So A and B are making up that sample. And what we're going to call the sample, this is our eluent. We're going to add more fresh liquid solvent that's going to carry it through as our liquid mobile phase. And now A and B are going to interact with the solid support that's coated with a liquid differently. Perhaps the liquid on the solid support is polar and our mobile phase is non-polar. Now the differences in the polarity of A and B, if we set up our experiment correctly, will allow them to partition differently into the solid supported liquid phase in our column. And we're going to encourage those to separate. And what we would see during the course of this separation process, if we could look at this, if this was a transparent column, we would see band separation. So if we call this our first step, we'll say at a short time later on this column, we'll call this time B, we're going to start to notice that A and B start to separate a little bit. Let's just say B comes out here. And they form these bands. Again, we might be able to see these if we had a transparent column. A and B start to separate. At first, they'll be almost on top of each other. And we'll discuss this a little bit later when we think about resolution. And as we flow more fresh eluent, more fresh mobile phase over here, at a later time, we'll move forward to C. We'll see that these bands start to spread out even more. At a later time, here's A. A is right here. And now B is starting to move further down. We'll assume A likes to interact longer, spend more time in the stationary phase, and B is moving quicker through the mobile phase. We can start to see how those bands are separating. Well, if we conducted this experiment until we can finally get complete separation of them, and we can collect them. We could collect them at the end of this column. We can collect separate portions that are now separate. We can collect a separate portion that has B in it and a separate portion that has A in it. And what we're saying has happened in this case is that this A and B has now eluted completely through the column. And we say that this is an elution that's occurred. So we can collect in our final stage we would have this, we'll call this D. In this stage, we would have B coming out, A still on the column to some small extent up here higher. And if we had a little stopcock or an opening at the bottom, and some type of collection vessel, we'd probably be able to collect B here. And at a later time, if we wait a little bit longer, we would be able to collect a separate portion that has our sample A in it. So that's essentially what we're doing in a liquid chromatography experiment. We're allowing analyte to separate based upon differences in how they partition between a mobile phase and a stationary phase, very similar to the liquid-liquid extraction that we discussed in our last lecture. So we could see that this is one method of separating, partitioning between one phase in comparison to another. So that's really not much different than what we did for our liquid-liquid extraction in our last lecture. Now we could collect these in separate containers and go measure how much of our red component, which is B, and how much of our green component, A, are there. But normally what we do is we set this up with an instrument that gives us a detection method, because all we're doing in chromatography is separating components. We need some other detector to tell us how much of that particular component is there when it comes off the column. Those are important features. How much, when it comes off, we can identify it and we can quantify how much is there. Now, there are, again, different ways we could measure the amounts of our analyte that come off that column. Probably one of the most useful is UV vis absorbance, such as we learned a few weeks ago. Another way, using a more expensive instrument setup, is a mass spectrometer. If you take instrumental analysis, you're going to be doing an experiment in GC mass spec, and you'll be using the mass spectrometer as your detector. But let's just show the general feature of what a separation would look like in terms of the instrument that we would be using. So the instrumentation involved for a chromatography experiment. This is for LC. Now for LC, we would probably have, well, not probably, but there'd be a pump involved. So this is a pump. Now what we use for our most effective way of preparing and introducing our liquid sample is to use a pretty high pressure pump. And this high pressure pump is an important component of what we call HPLC, high pressure, or we sometimes would rather refer to this as high performance liquid chromatography. Again, if you take chem instrumental analysis, you'll be using the HPLC, as we call it. Now, this arrow shows us that we're having a flow of liquid from our pump, and we would also have to introduce our sample. So this is often accomplished by using a syringe, or sometimes some type of flow loop, or we have a nice one in the instrumental lab, an auto sampler. So these are nice ways to introduce our sample. So we would have, usually it's a little inlet port that we would introduce our sample. And now on the PowerPoint, this is where our column would be located. So this is our column. Now our column will be designed to separate our analyte based upon different effects of each of the components that are in there. One component would prefer spending more time on the solid phase in our column or our stationary phase. It could be solid or liquid. And one of the components will want to spend more time in the liquid mobile phase. And as we showed earlier, using our bands, where our goal is to hopefully get separation of the different components that are in there. And at the end of this instrument, we have a method of detection. As I said, a very common method of detection is UV vis absorbance detector. There are other types of detectors. When we discuss gas chromatography, we'll discuss a different type of detector for that particular arrangement. Now, what the UV vis absorbance detector does is it generates some data that gives us a response of our analyte in terms of its absorption spectra over time, from which our different components start to elute from the column. And this creates a graph. The graph that we collect here at the very end, when we compile our data, is known as a chromatogram. So this is the general feature of a chromatogram. A chromatogram is simply a graph that shows detector response versus time that each of our analytes are eluting from the particular column. So let's think about our last experiment that I had written here before. Here's our response. Our response is our signal. And if we're using a UV vis absorbance detector, it's going to be absorbance. And we'll get a peak of absorbance for each of our analytes based upon the time at which they elute. So as we had before, we had a species came off first. The earliest species would show up first on our chromatogram, and a second species will show up at a later time. And that's generally what a chromatogram looks like. The chromatogram itself gives us a lot of information about what we're doing in this experiment. It provides information, the information that's really helpful about the chromatogram. It can answer the question, how efficient was our separation strategy? Can we resolve two or more species in a timely fashion? Time is money. A lot of these are conducted in industry, these separation strategies. Now, to answer these questions about the ability to resolve two peaks, and can we do it in a timely fashion? We're gonna look at two issues. First of all, differences in elution times of two peaks, and finally, we're going to look at band broadening. Why peaks broaden, and what that causes, an issue that it causes us as an analyst. So the first issue we're going to look at is differences in elution times between two peaks. So notice I have two peaks listed right here. Well, the elution time when they come off the column is really a good indication of what's happening with that analyte, how that analyte is interacting with the column in comparison to a different species that's in that particular environment. So let's draw a more complex chromatogram to answer some questions. And let's put some information on there and show how we can use the information that's given to us. So this is an example I have in the PowerPoint for today. And again, this is a slightly more complex chromatogram. I'm going to just use the exact one that I have in today's PowerPoint. So once again, we have a graph that gives us an axis of time versus our response from our detector. And what we're going to do is we're going to look at a little more complex situation. We have a peak here, and then we're going to look at three other peaks. They look a little bit differently on the PowerPoint, but hopefully you'll understand what I'm talking about when we look at this. Let's put some information on here. So let's assume right here at the beginning, this is our injection time. Right here where this black line comes down, we'll assume that we're starting this graph right when we make our injection. Now, most instruments have like a little electronic switch on it. Sometimes it's the touching of two metal plates that'll tell the detector that we're starting to make a measurement, and it'll give us a nice flat line where we start our measurement process. And let's look at a couple of these peaks down here, and we're going to put a line here. Let's just look at this one. We're going to call this TR. And we're going to define what TR is. Now, TR, for this peak that we're focusing on right here, it's the second peak. We'll discuss the first peak in a minute. TR is known as our retention time. Has a subscript R. That's our retention time. Now, the retention time, it tells us a little bit something about the time between when we make our injection and when our analyte reaches our detector. So it's really important. Notice different analytes based upon what column we're using, what our separation strategy is. We'll have different retention times based upon how they interact with the stationary phase and the mobile phase. And let's look at this other small species that I have here. Now, I have that on this graph, and I didn't label it yet because this is an important species. We're going to call this TM with a lowercase m. Now, what this small species, this small peak right here represents T sub m. Now, this small species is a species that doesn't interact with the stationary phase. In other words, this one comes off very quickly. It doesn't interact at all with our stationary phase, and it gives us some information about the time it takes for solvent to flow from the beginning of our injection down to our detector. And this T sub M has some terms that they call, sometimes it's known as void time or dead time. Now, this is the time for an unretained species to travel through the column. Real important information. Now, we're going to do an experiment a little bit later dealing with GC. A common non-retained species is CH4. I have it listed here. It's not used all the time, but it is commonly used in gas chromatography. So why is this important? Well, this void time, we can actually record what we call an adjusted retention time. Now, the adjusted retention time we're going to look at an adjusted retention time for our species of interest. And we're going to call this TR prime. Once again, that's for a species that we're interested in. We're putting a prime by it. The adjusted retention time is the time that our species travels from the point of injection to our detector, TR. And let's be consistent. These are like that. They have a peak, they have a little hat on them. Okay. TR minus T sub M. Now that's important, that piece of information. What this information tells us a little bit about, it tells us how long a retained species actually interacted with the stationary phase. Let's think about why. So let's just draw a little column moving like that. That's our column. Let's just go along with me. Hopefully it'll make sense. And we're going to look at a non-retained species, and we'll use a black spot for our non-retained species. And let's put an analyte up there with our red marker. Red marker's our analyte. And we start them at the same time. Okay? There goes our non-retained species. Goes right to our detector. Okay? Let's look at what happens to our species of interest that interacts with the solid phase. It moves along, and then it absorbs into the solid phase for a small amount of time. It equilibrates, and then may come back off into the mobile phase. And then a little bit later, it might start to go back into and interact with the solid phase. And then it comes back off, and then it moves down a little bit. And it would continue doing this until it reaches our detector. And we would recognize that the species that we're interested in, it takes a longer time to reach the detector because of all these events in which it's interacting with the stationary phase. So if we think about it, the time that it spends in the mobile phase is going to be the same amount of time that our non-retained species is in the mobile phase. But if we subtract that from the total time that our retained species is, it tells us a little bit about how long that non-retained red species actually interacted with the stationary phase. And that's really important information. So that's the reason why we use the adjusted retention time. It gives us information about how long an analyte is going to be experiencing the stationary phase. We have several species. Let's look at our other species. and what we use to help us understand a little bit about different species in that environment and some other information we get when we have more than a single species that's in that environment. We can look at another important piece of information. Let's just call this, and let's give these names now. Let's call this peak A and this peak B. And this is peak C down here. Well, what I can do, this is the retention time for A, and this would be the retention time for B. Another important piece of information we can get based upon our chromatogram is what we call a separation factor, alpha. Alpha, and we're going to use this as a comparator between two components. Alpha is also known as relative retention or separation factor. These are two terms you're going to hear for that. Alpha is simply the adjusted retention time for one species. Notice the prime, it's adjusted, it's accounting for the non-retained species divided by the adjusted retention time for species A. So that's what alpha is. Now, this tells us a little bit something about the separation of the two components, this ratio. Now, this ratio is always going to be greater than 1 because it's by convention, we take the adjusted retention time for a species that spends more time on a column over the adjusted retention time for a species that spends less time on the column. So this is always expressed in a value greater than 1. So this is another piece of information that tells us a little bit something about the relative retention of one species over another. We could also compare C to B, C to A, and that's other ways we can compare the column and how well we've separated different species. Another important piece of information is what we call the retention factor. And this is a lowercase k. So lowercase k. Remember, we discussed capital K was an equilibrium. This is not an equilibrium constant. This is called the retention factor. Now, the retention factor, it gives us information about a relative separation of an analyte versus the void time or dead time. So the retention factor for A, it would equal the retention time for A minus the retention time for our non-retained species divided by the retention time for that non-retained species. This is important also. Now, the reason why this is important, it tells us a little bit something about the effectiveness of our separation strategy and how we can compare it if we change conditions. For instance, if we change the length of the column, the retention time for our non-retained species is going to change, and so would the retention time for our species that we're using. But we can compare, using our retention factor, the relative efficiency of how one column separates under one length condition versus a different length. Another factor that we can change over the course of a separation, flow rate. We can change how fast we're flowing our mobile phase. If we increase the flow rate, well, A is going to come off faster, but if we compare this versus the non-retained species, we can get information about how this is affecting our separation by comparing retention factors. So those are really important. It's another important piece of information we get from a chromatography column. So let's try an example now. This is an example that I have posted on today's lecture PowerPoint. Let's leave this up. We'll be using this. And yeah, I guess we can get rid of that. So if this is today's example problem, and we're going to look at our data that's given to us, and we're going to look at a mixture of, it's composed of two compounds. We have compound A, and we have compound B. And we're going to separate them using chromatography, column chromatography. And the information that we have in this experiment also involves a non-retained species or an unretained. So we have an unretained species. I probably should have used non-retained. Sometimes I don't use proper English. Unretained species is also involved in this experiment. And I'm giving you their retention times. So the unretained species has a retention time. We'll call this TM, 42 seconds. Compound A has a retention time of 251 seconds. And compound B has a retention time 333 seconds. And let's calculate for each of them their retention factors. So there's A, and we can calculate a retention factor for B. So those are the retention factors that we would be able to calculate for each of them. So let's go in and calculate a retention factor for A first. Pretty simple calculation. It's plug and chug. We're going to put the retention time for A, 251. Minus the retention time of our unretained species. Divided by the retention time for our unretained species. And this is known as our retention factor. The retention factor for A is 4.98. Unitless number, seconds cancel out. We could calculate the retention factor for compound B also. Compound B, if we go through the same exercise, it would be the retention time for B minus the retention time of our unretained species divided by the retention time for our unretained species. Good. Let's also calculate the relative retention. So let's also calculate the relative retention. I'm going to erase this. alpha. Alpha is the relative retention. Relative retention tells us a little bit something about how the two components that we're focusing on are separated relatively. That's one way to think about it. And remember, relative retention in this case is going to be the adjusted retention time for B prime over the adjusted retention time for A. Or this is another way to do it. Since we've already calculated our retention factors, another way to report relative retention is simply the retention factor of B divided by the retention factor of A. Remember, it's always the factor that's larger over the factor that's smaller. Now, this is another way we can calculate it. Let's put our numbers in there and calculate a relative retention. 6.93 divided by 4.98. And I get a relative retention 1.39. So that tells us a little bit something about how well we're able to separate two species. Now, the next topic that we're going to discuss involves two features that, as an analytical chemist, if you're involved with chromatographic experiments, is efficiency and resolution. So this is a topic that we'll be spending time on over the next, probably today. We'll start into it, and this will be a really big topic that we'll be getting into on Monday. Now, efficiency and resolution for a chromatographic process two big features that we focus on when we design a separation strategy. And the questions that we're looking at is the effectiveness of our method. How well are we able to separate two species? And that's one question that we think of when we ask about its efficiency. So efficiency, we're focusing on the efficiency of our strategy. And we'll be spending some time on that probably on Monday. What we're going to focus on now is resolution. So this is the topic we're going to be finishing in today's lecture. The resolution of two peaks, or we sometimes call these bands. So that's another word that we use to represent the chromatogram, the bands that come off, the peaks that come off. And the questions, when we think about resolution, involve the topics that we just discussed, how well the retention times are different. That's important. Another important issue is band broadening. Peaks become broader the longer they're on a column. Let's go back to our little demonstration that we showed earlier. Remember, at the very beginning of today's lecture, we went through an experiment just to explain column chromatography. And we had, I'll try to get the colors correct. We had green and red. And let's think about, well, let's draw three of these. Let's draw three of these different times. what we might see. What we might see. I'm not going to put all the little dots in there. You all know there's a solid packing. So what happens at a later time? This might be a little bit different than our last image, but it's similar. Hopefully the gist of it is going to come out in this little discussion here. So let's imagine that we have a detector that's taking a picture and providing us with a chromatogram at time A, time B, and time C. We're taking a picture. We actually can do this in real life situations. We can actually have a column that gives us data real time. Real time data is really important, no pun intended. If we had a little window here, a window such as a transparent, almost like a cell window, and we could shine our laser in that cell window, remember the cell path, and we were able to measure the absorbance. That's actually what's done a lot using these types of instruments. We could look at our chromatogram at real time. And let's look at situation right here, A. A chromatogram collected there. We would have, notice B is coming off first, so make sure we get that correct. This red one's coming sooner, and it would be represented by that. But guess what? The green guy is right next to it. And we're going to get something that looks like that. We get this peak that's not well resolved. We don't have separate red band. We don't have a separate green band. They're overlapping because they've not yet quite separated in the column. And we're getting poor resolution. So this one right here is poor resolution. So let's look at, this is A, because we can see they're still pretty close to one another. So let's look at what happens here at B. The bands start to separate a little bit. So we have a band or a peak due to B, and it starts to come back to baseline. Notice when it comes back to baseline, that means our detector response is going back to 0. But guess what? It doesn't reach 0 because all of a sudden green guy comes off and it gives us a response. And we get something like that. Now notice the resolution's a little better, but we're not getting what we call baseline resolution. This response is not returning back to the baseline before we start to see our green band. So we are getting still non-baseline resolution on B. We'll call this non-baseline. That's something we try to achieve. Baseline resolution is really important. And we'll give a number to it. We'll actually quantify it. Let's look at what happens if we took a picture under C conditions at that time. Let's look at C. I'll put C over here. C is the one we wanted. So here's B, or our red sample. I'm not going to give these a letter. Here's our red sample. Notice it has a Gaussian curve. It looks like a bell curve, like a distribution. And then here's the band for our green component. Notice their baseline resolved. In other words, we're getting a response for our red band, which represents one of our analytes coming off, and we're measuring an absorbance for that one. The detector no longer sees anything. we get zero absorbance, and then we get an absorbance that's occurring for our component that comes off second. And there's two features that we should recognize here. First of all, this is what we call baseline resolution, as I just explained. We're coming back to baseline, where now our detector is no longer detecting any absorbance, and all of a sudden our second component comes off, and now we're getting a response from that particular substance. Another issue that we see in these, and you should recognize, is that the band that comes off later starts to broaden. It starts to get bigger. Now, we're going to discuss this a little bit in more detail on Monday. And the reason why these bands broaden, one of the big things here is diffusion. And that's an important factor that we're going to be discussing in Monday's lecture. But what we want to discuss here is a measurement of our separation in terms of resolution. That's really important. And we're going to discuss the resolution of these two peaks. And we have a way of describing our resolution, actually a mathematical expression. Resolution has R with a lowercase subscripted s. Resolution is simply a measurement of separation of two peaks, and it can be defined by an equation. Resolution 2 times the difference in the adjusted peak retention time of one component, and we'll just call this B, minus the adjusted retention time of another component, we'll call that A, divided by their baseline width added. And we've discussed retention time. Let's understand what we mean by baseline width. So in this case, baseline width for this component, well, I'll draw it bigger just so we know. Baseline width. So let's look at two components. Again, they have nice Gaussian curves in an ideal situation. And these are the one that comes out a little bit later is usually a little wider. Baseline width would be the width at the baseline of these two components that we have in this situation. So in this case, this will be the retention time of the later peak. So we'll call this B and this one A. And this would be the width of B, and this is the width of A. And we use this definition of resolution to give us some information about how well we've resolved two peaks in a chromatographic separation strategy. And normally what we want is we want a resolution where we get called baseline resolution, and we want a number to that. The number that we strive for in many cases is a resolution of 1.5 or greater. So for this example right here that I have drawn at the end of this experiment that we had, this is probably a resolution greater than 1.5. And that's what we call a baseline resolution, when we get that situation in which we get two peaks that are well resolved. Let's go through an example of using some information. Let's leave this equation up here. And here's an example from today's PowerPoint. We have a chromatographic analysis of two components. One is lemon oil, and lemon oil has a component in it named limonene. And limonene has a retention time, we'll say TR. We'll call this limonene. 8.41 minutes. And it has a baseline width of 0.64 minutes. So notice the retention time and the width are both on the same axis, and they're in time units of minutes. And we have another component. The other component is called gamma terpenine. And we have a retention time, I'll just call that retention time of gamma, 9.5 minutes. And this has a width. The width is 0.96 minutes. Again, the later peak usually is a little wider. And our question is, our resolution of 1.5 is desired. Should we spend more time improving our separation strategy if this is the data we get from a chromatographic experiment? Let's put our data in here and let's calculate what our resolution is. Let's put these numbers in here. Remember, this is going to be the retention time for our later species, 9.5, minus the one that comes out earlier. And these are both in minutes, divided by our widths. This one is 0.96 plus 0.64. And these are both in minutes. So our units cancel out. And we get a unitless number that we can use to compare our resolution to a described criteria. In this case, I calculate a resolution that's less than 1.5. So for these people conducting this experiment, they should go and find a better way to improve their separation strategy. This suggests that we're not getting baseline resolution, and we might be able to make an improvement in what we're doing for our experiment. Now, what we're going to pick up with on Monday is discussion on the efficiency of a separation, a chromatographic experiment. And what we're going to introduce is a topic called plate theory and understanding the effects of diffusion on peak broadening and how that can be a limit that we need to address in terms of our ability to resolve peaks and make a more efficient separation strategy. So have a good weekend. Good luck, and see you all next Monday.